Hi there, welcome to the 34th episode of the Synth project, where we are building a synth together. It has finally come the time to take care of the last element of the control voltage processor, the LED-based voltmeter, a device that will allow us to take quick measurements of changing voltages, allowing us to fine-tune the signals that we need to control the sound produced by the synthesizer. Let's get into that right away. As you might remember from the introductory episode of the CV processor, the Voltmeter is going to be a simple instrument using a strip of 10 LEDs organized in a column to measure input voltages between 0 and 10 volts in two possible ranges. The first range will go from 0 volt to 1 volt, and therefore each LED will represent an increment of 0.1 volts. The second range, selectable with a simple switch, will go from 0 volts to 10 volts, therefore having each LED representing an 1 volt increment in the column. The device will also have a through output, so while we measure the voltage, we can also use it to control some other module of the synth. The schematic of this device is very simple, since it is built around the IC LM3914, which takes care of handling the voltage measurements and the control of each of the LEDs on the panel. The signal comes in through the H16 header, and it is immediately split in two parts. The wire on the bottom goes directly into an op-amp configured as a voltage follower, which provides the signal for the through output. This output will basically replicate the input signal so it can be used while we measure it. The wire on the top, instead, goes to a voltage divider made of R25 and R26. This divider cuts the voltage in half to adapt it to the range of the IC, which is really 5 volts. This means that when the input signal is 10 volt, it will be presented as a 5 volt signal to the input of the LM3914, which will indicate the maximum amount of 10 volts. In addition, the signal at the output of the voltage divider goes through the op-amp U5.2, which is half of the LM358, of which we have already used the other half for the through signal. U5.2 is configured again as a DC amplifier that works with two possible gains, selected through the switch SW2. When the switch is in the upper position, the amplifier will have a gain of 1, being essentially a voltage follower, and in such a case the range will be the 0 to 10 volts. When the switch is in the lower position, it will take the feedback signal from the voltage divider made of R27 and R29, causing the op-amp to have a gain of 10. In this condition, the range of the voltmeter will be from 0 to 1 volts. Resistor R28 defines the amount of current flowing in the LEDs according to the formula described in the LM3914 datasheet on page 2. In there, you can see that the resistor between pins 7 and 8 directly defines the current flowing in each LED. The tuning of the voltmeter is done through the multi-target input RP7, which, along with R28, defines the top range of the voltmeter. This is also documented in the LM3914 datasheet in the same page 2, as you can see here. Pin 9 of the LM3914 defines whether we have a voltmeter presenting a whole lighted-up column of LEDs or just a single one LED representing the specific voltage. In this case, I decided to use the columnar representation, which is more visually appealing, at least to me. If you prefer to have a dotted display, you just need to cut the wire that connects pin 9 to the plus 12 volts on the PCB. Finally, the electrolytic capacitor C14 is used to filter out the noise introduced into the power line by the turning on and off of the LEDs. Such power line, by the way, is the one at plus 5 volts. Since this voltage is available on the power rating of the synth, I decided to use it to reduce the power dissipated inside the LM3914 when the LEDs are turned on. And here we are, one more time, with a breadboard where I have mounted all the previous pieces of the CV processor. The new LED voltmeter is mounted here on the right side column. Further on the right, I put an extra support for the range switch, with the 10 volts on the upper position and the 1 volt on the lower position. This one is the IC that contains the two op-amps, and this instead is the LM3914, which is the core of the voltmeter functionality. This IC controls these 10 LEDs based on the selected range. The calibration of the voltmeter scale is done through this multi-turn trim pot. Here on the upper side we have the input connector and the through connector. We can start running our tests right away, and the first part is the calibration of the scale. Let's do that. So let's start powering up the circuit. To run all the tests I have connected my function generator to the device input. The function generator is currently set up to provide a square wave with a peak-to-peak amplitude of 1 volts and an offset of 0.5 volts. This way, the generator will emit an all-positive square wave going from 0 volt to 1 volt and vice versa. The frequency is set to 0.1 Hz, slow enough to allow us to do the tuning with no rush. With these conditions, you can see that when the LEDs turn on, they are not all lighted up, and that is because we haven't done the calibration yet. The first part of the calibration needs to be done in the 1 volt range, and that's why the generator is set to that peak-to-peak amplitude. Given the output of the function generator, the LEDs are supposed to be either all on at the same time or all off at the same time. So what I'm going to do now is to wait until the LED column turns on, and I will start adjusting the multi-turn trim pot until all the LEDs are on. Let's start adjusting the trim pot. Now another LED is on, but there is still one off. So they are all off now, so we need to wait until they turn on again. Let's keep rotating the trim pot screw. The top LED needs to be turned on too, but we need to continue rotating the trim pot screw until the LED is fully lighted up. We cannot just stop when we see it turning on. Okay, this seems to be fine now. At this point, if we change the range to 10 volts, we should see just the first LED of the column turning on and off. However, if we go back to the function generator, we can reconfigure it to output a signal that is 10 volts peak-to-peak with an offset of 5 volts. Let's do that, and let's start with the offset so the input signal will always be positive. Now, if we go back to the LEDs, we should see that there are 5 or 6 LEDs on, depending on the position of the square wave. Unfortunately, we have 6 or 7 LEDs that go on, and this means that we didn't do a good job before when calibrating the scale. We can fix that by readjusting the tuning of the trim pot a little bit. And here we go. We now have either 5 or 6 LEDs. Let's now go back to the function generator to double check that the new tuning works also in the 10 volts range. So let's bring the offset to 0.5 volts and let's switch the voltmeter range back to 1 volts. And again, the tuning is not perfect as the 10th LED is not on anymore, and this means that we need to make again a few adjustments. Basically, we need to go back and forth this way until we obtain the correct behavior. Once that is done, we move again to the 10 volts range and we adjust the generator to output a 10 volts peak-to-peak voltage with a 5 volts offset. Now we check the LEDs. They are currently all off. And now they are all on, so the tuning seems now to hold on correctly. We should now make sure that we can also measure all the intermediate values, at least visually. To do that, we can change the shape of the signal emitted by the generator, and instead of using a square wave, we use a triangular wave. With such a signal, we should be able to see the LEDs turn on one at a time, at a linear pace, and once they are all on, they should go back off one by one until they are all off. Then the cycle should repeat unchanged. Let's see if that works. And yeah, look at that, the LEDs now behave exactly as expected. They go on 1 volt at a time, and then off, also 1 volt at a time, which means one LED at a time. Let's try now with a sine wave, which should end up with faster speed of the LEDs toward the center and the edges, and a slower speed in between those places. And yes, that works too. At this point, we can safely say that all the tests have been successful. And this concludes the design and the lab testing of the whole CV processor. In the next episode of the series, we will finally go through the assembly and installation of the whole module, and also its installation in the Synth rack. To avoid missing this episode, as well as any other future video, please remember to subscribe to the channel if you haven't done so already, and also make sure you have your notifications enabled. See you soon in the next video, and as usual, happy experiments!